Project Officer at ETN Global, the membership association based in Brussels that is coordinating the Robinson project. Today we're delighted to welcome you to our fourth episode of the Robinson webinar series, where we will discuss the energy management system of our project, and more in detail we will see the activities carried out by our consortium, in particular by University of Genoa in Italy, in the domains of integration and simulation activities. Mario Ferrari, professor at University of Genoa, and Simone Maccarini, researcher at the University of Genoa, will be presenting today the topic. So we'll have a presentation followed by a question and answers session with all the participants. We kindly ask you to mute yourself during presentation, and with the question and answers, please feel free to raise your hand and participate in the interaction. We'll then conclude with a few questions also to you participants. So with this, I intend to conclude my introduction, and I give the floor to Mario and Simone for their presentation. Thank you.
Thank you, Nicola, for this introduction. So, ladies and gentlemen, good afternoon. The presentation today is related to the energy management system developed in the Robinson project. So I would like to start with the motivation slides and to a brief description of the concept of the Robinson project. The models developed and validated in our activities at the University of Genoa to focus final attention on the energy management system. Then we have slides about results, starting from simulation and then switching to the laboratory activity performed in cyber-physical mode. And so we will have some experimental results to conclude the webinar. So the motivation is clear here. Maybe I think it could be clear to a lot of us, but for sure in case of people approaching to the problem, it's important to remember that a polygeneration grid is a complex object with different distribution grids, maybe in this case an electrical grid and a thermal grid, but we can have also cooling energy grid, water grid, and so on, so very complex. In this case, we can imagine to have just electrical and thermal grid. From the electrical point of view, we can have different systems able to generate electricity. For simplicity, we have three generators, but we can extend the option, the layout to tens of generators. We can have different users. We can have prosumers, so entities able to generate or consume depending on the hours or depending on the seasons, and so on. We can imagine solar panels, for instance. Then we can integrate electrical storage devices. We can start to imagine batteries, but we have also more complex objects like systems based on hydrogen storage, for instance. So electrolyzer, hydrogen storage system, user fuel cell, and so on. So very complex devices. Also, from the thermal point of view, we can have a similar situation with a lot of generators, a lot of users. We can have integrated generators with electrical generators in cogeneration mode. We can have also here prosumers, and we can have thermal storage devices that could be simply water tanks or more complex devices like based on phase changing materials, thermochemical devices, and so on. In some cases, especially if we have islands far away from the coast and so on, we can have also the option of operating without a connection to the main electrical grid. For sure, this increases the complexity of the system because the imbalance between generation and production must be fully satisfied by the storage systems in real-time mode. Just to give you an example of the necessity of managing these grids with the proper real-time optimizer is shown here with an example with the T100 machine. The data comes from the test that we performed in our laboratory at the University of Genoa in the Savona campus. So for considering natural gas for the price reported here and for a 24-hour test analysis, we can imagine to have a demand, a power demand for the electrical point of view as reported in the bottom left of the slide. We can satisfy the power demand just following the demand like this. So we can manage the T100 machine producing 20 kilowatt about during the night, increasing the load up to about 90 kilowatt at 8 o'clock. Then the load is reduced to about something about 70 kilowatt at 12 and so on. Okay. This is a standard management approach without any particular intelligence to manage this load. Another option could be like this. If you have the possibility of storing energy, maybe you can imagine a battery, we can decide to operate the T100 machine at full load condition during the central part of the day between 8 o'clock to 9 o'clock, more or less, 9 p.m. Just to use the machine at the nominal anyway, at the maximum efficiency. But during the night, when the demand is low, instead of operating the machine at low load, that means at low efficiency, it's possible to switch off the machine and to use the stored electricity energy in a battery, for instance. With this simple approach, is simple because we are talking about just only one generator, but with just this simple difference, we have a reduction of cost for this 24 hours of about 17%. So this is important to motivate, to highlight that the development of and an application of an energy management system, so a real-time software able to optimize decide the on-off status and the set points to the prime mover, it's important to reduce, minimize the costs, or reduce or minimize the CO2 emissions or other targets that could be interesting. In this case, we selected a simple objective approach, but it's possible we have also multi-objective approaches reported in literature and so on. So now I would like to leave the floor to Simone. Simone, are you here?
Yes, Mario.
Okay,
can you hear me?
You can present the Robinson project with the Egenroy layout and the simulation activities. Now I'll continue with the laboratory part. The floor is yours, Simone.
Okay, thank you, Mario. So thank you, everyone. And just starting about so more specifically with the introduction made by Professor Ferrari, we had a look during the Robinson project at the implementation of this concept, this general concept, especially in the Egeroy facility. And so we developed an EMS to be installed later in this facility studied by the project. And so we perform a simulation at Luigi using these parameters that has later been implemented in the actual facility. So what we consider in the facility at the Eggeroi site was constituted by a CHP microturbine of 400 kilowatt electrical, a steam boiler already present with a 22 megawatt thermal power, 2 electrolyzers to be installed, and a gasifier, and a renewable energy source park constituted by a wind turbine and a small PV. And later on, also a storage hydrogen, a fuel gas mixer to mix the fuels for to be injected in the CHP microturbine, and of course a connection with the electrical main grid. Next slide, please. Mario, can you move? Okay, thank you. So first of all, we needed to validate, to implement and validate in our model the different components. So different components were implemented in the Transio tool, which is developed internally to Luigi in MATLAB Simulink. And so we implemented different components as the CHP, the electrolyzer, and so on. And we aim to validate them using mainly part load and dynamic data from the manufacturer with a black box approach. So receiving data from the partner and implementing them in a simple model, simplified model, implementing a first order delay behavior, which is common practice in dynamic simulations. So here you can see in the bottom the validation of the experimental response to a step input, step variation input, and the model in yellow, the model response as a first order delay. Next slide, please. So this is the general structure of the energy management system and its connection to the smart grid. So basically, the energy management system is constituted by a decision maker plus a model predictive controller. So, and the energy management system basically receives the curves of demands in thermal and electrical power and the costs of electrical power and fuel and hydrogen. And so aim at optimize a strategy of dispatchment and usage of the resources in the smart grid. Next slide, please. So more in detail. We see that the first component of the energy management system is the decision maker. So this is the component in the energy management system that actually receives the demand and cost curves and compute a best strategies using an algorithm as can be shown in this figure. And so depending on the what are the curves, what are the expected power to be produced, and what is the expected power to be delivered to each component in each moment, the decision maker provides an optimized solution within a 15 minutes time step using an algorithm using a pattern search type algorithm, aiming at minimizing the cost function, which is also reported here in this slide. So balancing basically the electricity production of the CHP and the usage of the grid, and also with the cost of the fuel itself. Next slide, please. So once the main strategy is decided by the decision maker, this is conveyed to the actual controller, which is the model predictive control, which is inside constituted by an actual model predictive control, an actual controller, and an observer, which basically, as the name says, it actually observes the actual system, which in the first simulation was indeed inside the model, but in the cyber physical, then and in the implementation, it will be the actual model, the actual plant. So it uses the measures of the actual plant to determine the state of the system, and so use the information of the state, of the actual state of the system, and together with the optimized strategies provided by the decision maker, aim at constituting a best strategy to reach, to control the plant and reach the optimized setting point for each component at each time. In this specific case, it was used a prediction horizon of 40 seconds and a control horizon of 1 second. Next slide, please. Next, okay. So in parallel to this, also we said that the our smart grid is also constituted by an hydrogen management system, which is basically constituted by a vessel of 40 square meters, and the system aim at controlling these two different pressures. So either higher pressure of 40 bar or lower pressure of 22 bar, and these allow to fill in or the vessel or use the hydrogen depending on the basically on the cost during the day. And so these to implement also the control of this type on the hydrogen, it was necessary to constitute a similar model predictive control as it was shown before, but dedicated to the hydrogen management system. And so this was linked to the general EMS through the same use of the optimized strategy and the demand curves and the cost curves as well. But it was implemented in a separated and parallel MPC. Next slide, please. Okay. So at first, at this point, I can show you some of the first results of the simulations that we perform, and then Professor Ferrari can show you the application of the same MPC and EMS in general to a cyber-physical approach. But for what concerns the first simulation results, here are listed in the table the costs and the size of the components that were used in these first simulations. And mainly two types of simulations were performed in this work and are reported here. The first one is a comparison test between the usage or not the usage of a EMS of this type. So with respect to a no EMS scenario, when the CHP follows only the electrical demand and the boiler kick in when the thermal demand is not satisfied, and the electrolyzer are always run at minimum load, so without considering the actual cost variations during the day. And also, second simulation is a robustness assessment that was conducted on a 24-hour time span, in which it was simulated the failure of some controllers, and so the reliability and the resilience of the EMS in managing these wrong, basically, signals and how to manage them without compromising the function of the smart grid itself. Next slide, please. So here it can be seen in the three figures the production of the electrical power, the thermal power, and hydrogen management in the smart grid. How it can be compared the performance of the EMS system with the normal straight line and the no EMS scenario in the dotted lines. So as I was saying before, for what concerns the electrical power, the no EMS scenario just manage the plant or the smart grid in the CHP just to follow the electrical power requests, while in the EMS scenario with these power sizes that were available, that were decided for the specific smart grid in Eggeroi, it was shown that in this period of time, the CHP is instead run at the maximum power, a rated power, and to allow the excess electricity to be sold to the grid. This was done also the same response, the same time span can be seen in the response of the thermal power, in which it can be seen that especially the core. So with respect to the increasing demand in thermal power, which you can see in blue in the central slide, in the central figure, the EMS scenario allows a later start of the boiler, as you can see with the two green lines, with respect to a no EMS scenario, which, as it was in the specific case, which allows to reduce the consumption of fuel, and so the production also of CO2. This was because, of course, it was higher, the CHP thermal production to be used by the demand of the smart grid. As well as also you can see a different response in the hydrogen management, where we can have a higher production of hydrogen, especially at the 5th hour, because the cost was allowing that to be of revenue. Next slide, please. So numerically, some comparison between these two scenarios were indeed evaluated by three main key parameters. So the costs were reduced by 30% using so in the analyzed scenario with the usage of the EMS with compared with the no EMS scenario. The electrical efficiency was higher, both for the CHP system, which was run at more time at the rated power, as well as for the entire system of the smart grid. And lately, also the production of CO2, of kilograms of CO2, as computed as shown in the formula in this slide, was decreased by 60%, mainly because of a reduction of the usage of the boiler, thanks to the CHP thermal power. Next slide, please. So finally, as I was saying, here is shown also the simulation regarding our robustness assessment. So this was simulated errors in the signals or cyber attacks that basically were reducing the signal values to 0 kilowatt for what concerns the powers, or the standard, let me say, value of 1 bar for signaling pressures. So these graphs show basically for the electrical power that no influence was seen on the CHP behavior. And so the CHP kept on running following the main strategy without, and was able, the EMS was able to compensate this error in the signal. Contrary to this, the boiler response was affected, as you can see in the green line in the central figure, but was able to be restored quickly and to follow again the optimized strategies, and so able to not affect the costs and the efficiency of the whole management strategy. And for what concerns the hydrogen management system, instead, again, the pressure in the vessel was not hugely modified, and the controller was able to restart immediately after the simulated failure of the signal. Next slide, please. I don't remember if there's one more.
Simone. Thank you for this presentation. I would like to go on with the part related to experimental activities performed in the Savona campus of the University of Genoa. So,
thank you, Mario. Thank you all.
Thanks. So, following the simulations presented by Simone, before going in the real demo site of the Robinson project, that is the Genoa site of the Prima Protein industry, it's important to continue the check and the validation, the MS validation, switching to some real data. And the management of some real components. For sure, at the laboratory level, it's not possible to have the access to the entire network, so the entire technology is available in the Robinson project, because this is the demo site. So after the installation of everything in the demo site, we will be in the real site. However, in the laboratory of the University of Genoa, we have CHP, microturbine, and PV panels, thermal grid, the connection to electrical grid, the possibility of generating thermal load locally, and so on. So we performed tests in cyber-physical mode. Cyber-physical mode, it means that the software, so the hardware that we have in the laboratory, with some software for components not physically available, like, for instance, the fuel mixer, the hydrogen part, so electrolyzer, hydrogen tanks, and so on. So here on the left part of the slide, you can see, okay, the software is the boiler, the wind turbine, the electrolyzer, the hydrogen storing tank, gas mixer, and then the hardware is a part of the grids, is the CHP and the PV panels. So in real-time mode, we have the transfer of the calculated on-off signals and electrical set point value from the EMS to the CHP that we have in laboratory. In real-time mode, we have also the measurements from the field electrical power produced by the CHP, the thermal power produced by the CHP, the fuel flow, and the electrical power produced by the PV panels. This is important because thanks to the interaction with the real measurements, we were able to check some problems and to improve the stabilization of the MP, the MPC, and so on. Because at the beginning of the test, the initial 15 minutes failed due to the fact that the MPC was not so much stable to, so it was stable for the simulations, but it was not enough stable for the management of the real plant due to oscillations of signals, maybe an additional delay due to the pipes that we have and so on. So after some operations for improving the EMS, we performed the tests in cyber-physical mode for 26-hour case, so 1 day plus additional 2 hours, because this was a target, an objective requested by the Robinson project. So here in this slide, it's possible to see the input data that we considered. In this case, we consider 80 euro per megawatt hour for syngas cost. We know that it is a very high price, probably not realistic, but it was selected to have a price that produces a good impact on the EMS in terms that the EMS changes a lot the operative condition of the system, because a low cost of the syngas produces no movement, so generates an output like a CHP at maximum load for the entire 26 hours. And this is probably not so much good to check the performance of the EMS and its robustness. So in the bottom of the slide, it's possible to see the results compared with the no EMS case. So the no EMS case is a simple management without a real management. So the CHP is managed to follow the demand second by second up to the maximum of production. When the CHP is at maximum, the missing amount of electrical power is obtained by the grid. For the thermal point of view, we are following the same approach, trying to move the boiler to satisfy the demand. However, the boiler response is not instantaneous, so the delay is about 1 or 2 hours. So you can see this mismatch between the demand and the response due to this aspect. From the hydrogen production point of view, the electrolyzers were maintained at the minimum production, 80 kilowatt both over 500, just to satisfy more or less the demand. However, we have a decrease of the hydrogen storage but it's a choice for sure, because other choices can be implemented. So switching from the no EMS case to the application of the EMS, that means the real test performed for 24 hours in cyber-physical mode, here it's possible to see the results obtained from the electrical part. So the EMS generates management of the CHP, that it's managed at low load when it is not profitable to sell electricity because of low price of the electricity. But the CHP is not switched off when the boiler is not active, because it is maintained. It is necessary for satisfying the minimum thermal demand that we have. When it's profitable to sell electricity to the grid because of high price of electricity, the sell-by ratio in the terms of cost is 1 in this test. The CHP has been moved to 100%, that means 400 kilowatt. Then when again at about the hour number 14, 15, again we have low cost of electricity price, the CHP in this case is switched off because we have the boiler, so all the thermal demand is satisfied by the boiler. And then after the hour number is about 16, it's 4 p.m., the CHP switched on again because profitable, selling electrical energy to the grid, and this is maintained up to the end of the 24 hours. On the thermal point of view, we can say the effect on the EMS. So thanks to the application of the EMS, it's possible to better follow the demand, thanks to the MPC that is a good controller for taking into account the dynamics. The gap between the generation of the boiler and the demand is the generation with the CHP. Finally, on the right side, we can see that the behavior changed a lot for the hydrogen generation point of view, because thanks to the application of DMS, we are able to compensate the demand of hydrogen and to maintain the hydrogen content in the tank at a good level. Okay, then we can.
Could you please accelerate on the last few slides, please, so that we also allow a bit of question and answers? Thank you.
For sure, we can switch to the second test operated at €5 per megawatt hour. This second test is more realistic for point of view, for the cost point of view, but you can say that the EMS maintained the CHP at maximum for the entire 26 hours, so not testing the robustness too much, but anyway, obtaining good results for comparison. And so here we have the comparison of the experimental results showing interesting cost decrease for both cases. For the €5 per megawatt hour case, we have minus 8.3%. We had an increase in efficiency that is very evident for the €5 per megawatt hour case. But it's important to highlight that even if the objective of the objective function is the cost minimization, we have also decrease in terms of CO2 emissions with an important impact on from the environment point of view. Since the one target of the Robinson project is the replication of the EMS for other cases, we performed tests in cyber-physical mode also for other two cases, the Crete district of the Western Islands, including the prime movers that you can see listed, and the Mana district for the Crete island with other kinds of prime movers. In both cases, we obtain an interesting decrease of costs, as shown on the right part of the slide, and especially for the Western Island, we reduce a lot, close to zero, the emission of CO2, and we decrease the cost of more than minus 40%, and this is very important as obtained performance. So in conclusion, we validated the EMS first of all with simulations, then in cyber-physical mode. We proved and we confirmed EMS robustness, showing that in case of errors in measurement, everything remains stable, and the performance obtained, we already discussed them, were interesting for the Garroy cases, but also in cases in the replications cases, as already highlighted. So thank you for your time, and I'm available for the questions in the Q&A session.
Thank you, Mario. Thank you, Simone. Very detailed presentation. So I'd like to open the floor for any questions you may have to our presenters, or even any remarks you may have. Alessandro, I see your raised hand. Yeah. Please go ahead.
Thank you very much, Nicola, and thanks, Mario, for the presentation. It was very insightful for me. My name is Alessandro Enzo. I'm part of Baker Hughes. I'm a hydrogen service platform manager, just to introduce myself. Two questions. The first one is about, let's say, what was the focus of EMS? Because in the end, you got pretty good results, both in cost reduction, efficiency increase, and also CO2 reduction. The aim should be the first one.
Yes.
Levelized cost of energy, I would say.
No, variable costs. So
Okay.
the objective function includes variable costs like electricity, fuel cost, and operating and maintenance.
So was cost reduction the first driver?
Yes,
I think so.
yes.
Okay.
It is a choice. It's possible to change the objective as we prefer.
And this triggers the second question that was about, could we work on CO2 management? That was another interesting results based, let's say, on the outcome, no?
Yes, it's possible. Now we implemented a cost function, but it's possible to implement a CO2 emission function. And so what we obtained is the objective is the reduction of costs, the decrease, the minimization of costs, and the effect on the efficiency and the CO2 is a side effect. So we, after the results of both simulations and experiments, we evaluated and compared the efficiency and the emissions of CO2. For sure, we are not sure that the CO2 emissions are minimized, so it's possible to change the objective function, putting a CO2 objective function, and this is another kind of management approach.
And last question that was about, just to understand if I correctly understood about time for simulation. I assume this is a closed loop, okay? It's not an open loop, so you don't provide suggestions, simply the system acts, okay, based on the simulations, and so is everything automatically done, I suppose. Yeah, and therefore time for, let's say, the simulation for the forecast, I would say, how much time is needed, what's the time frame that you have in front of you, and what's the time of the implementation when, let's say, you identify the right solution. Just to see, because there were some numbers, I don't want to, let's say, miss this concept at this point.
Okay, I can try to answer. So the simulation timing is fast because it includes simple models based on interpolation maps, first order delay, and so on. So the 24 hours in simulations are calculated in few minutes. But I would like you mentioned about the forecast and so on. In reality, for what we need a forecast is just for the electricity cost, because the hydrogen, we have a storage. The hydrogen storage is managed on the basis of a scheduling. So 24-hour costs forecasted. The forecast is not done by the model, so we can take the numbers of the previous day, the day before, or the number of the same day for the year before. So this is the model is not doing a forecast of cost. This is necessary to decide when it's better to charge the hydrogen vessel or to discharge it, because it is a storage and we need a scheduling. But for the rest, we do not have any forecast. So in our model, we implemented demand for 24 hours, in reality 26 hours, and for both thermal, electrical, and hydrogen demands. But in reality, this can change in real-time mode. So this can be an input, and if in a specific time I have a peak of demand, so the model can accept, and it is a real-time model that the real-time MS is able to compensate everything. I hope to have answered you.
Yeah, I think so. Thank you.
Thank you, Alessandro. Is there any further questions? We still have about 11 minutes. So any questions you may have, Mario and Simone will have plenty of time to respond to your questions. In case you have questions, please raise your hands. But I do not see none. So I would like to actually ask both of you, Simone and Mario, a question, because I did see this interesting graphics indeed at the very end with the reduction of the greenhouse gases emissions with certain prices, with the global comparison and also the comparison of our follower islands in Crete and in Scotland. So on the development of this model for the energy management system, what is the utmost recommendation you would like to share to any sister projects or similar projects to those of Robinson? What are what is the most important recommendation you would like to share indeed?
Okay, I'll try to start to answer, then if Simone would like to add something after my answer. Okay, first of all, the results presented here are case sensitive. So it's not possible to say that an EMS is able to reduce the cost of 30%, 20% at all, because we need to, so it depends on the case. Because it depends on the demands, it depends on the prime movers installed and so on. It's important to know if in the case, in the smart grid we are considering, an optimization is reasonable, because in some cases the optimization is obvious, because we have seen the case of €5 per megawatt hour. In this case, for sure, if we have the CHP that can use so the option is electricity from the grid that has a cost, or electricity from very low cost fuel due to an internal recycling of resources or utilization of local resources. Probably in this case there is nothing to optimize, so it's obvious. Okay, so it's important to have in the grid, in the district, consider some degrees of freedom, because in some cases it's the option is, or maybe we can install a hydrogen generation storage system, but the comparison is with CHP that uses syngas. In this case, it's horrible to use electricity from the grid that has a high cost for generation hydrogen and so on, if we have the connection with the grid and so on. So we need to consider the situation, and the optimization depends. So first of all, we need to have the degrees of freedom. Okay, it's an important option. Then another aspect to consider is we need to have the possibility of operating in real-time mode on some prime movers. That I would like to answer in terms of at maximum hours. Okay, the CHP answer from the electrical point of view in fast mode minutes. From thermal point of view, 15 minutes. Microturbine has an answer like this. A boiler is lower, so a megawatt boiler is lower, but maybe the answer is about in terms of a couple, 1 hour, couple of hours. For sure, if we are considering the syngas generation, probably the gasifier normally is managed at a fixed point. So in this case, normally we have the gasifier, production of syngas, and we have a storage device of the syngas. In this case, the operation, the management on a gasifier that is managed at a fixed point, and the answer, the modification of the related condition is longer in terms of maybe 1 day. In this case, the optimization is so available, discussable, because so we need to check what to do in this case. Then other things to do, for sure, the development of DMS, even if we try to have large modularity, if you like to have something physical based, for sure it's important that the switch to a system like this in a Heroi to a system with 10 microturbines, 20 boilers, more PV panels and so on, different hydrogen technology, it's not easy. So it is necessary to have a minimum amount of time for developing the new MS technology. And it is important to have some experimental results, because in our EMS we have the MPC controller that is good for taking into account the dynamic of the components, but for implementing it, it's necessary to have an idea of the dynamic response of the component. So it's better to have experimental results, or at least some numbers, something from the implementation, just to calculate a minimum amount of delay of this.
Thank you, Mario. Is there anything, Simone, you would like to add to just what
Yes, for sure.
Mario
I'm
said?
glad to transfer the floor
So,
to Simone for completing the answer.
Yes, maybe just a few words following the path of what Mario said. So just an idea of, I think that in the specific case, we had some constraints, of course, that were needed to be respected, given by the Egeroi site. And so with a huge difference in the rated powers of the thermal and electrical part of the smart grid, for example, even in this case, because of the characteristic of the site, the EMS proved to be more efficient with respect to a traditional control. So I think that a suggestion is to use, of course, a predictive control where necessary. It can enhance, of course, the efficiency and of any kind of these sites of these plates. And I think that even where possible, maybe in this case was not so much possible for this project, but even a more holistic approach in the maybe definition of a new site. So if it was given to, like for this example, to extrapolate something for new project, for new sites. So even a more holistic approach that can reiterate using the results of EMS simulation usage and change where possible, where properties and investment allows to so integrate better results. And I think it is even possible to achieve better results than the one showed. So as well as also this site as well can be further improved. So,
good question. I also asked it before. We're 4 o'clock. Saskia is leaving now. She's gonna maybe she already left, honestly. She wanted to take the train now at 4. I'll stay another hour. I would be up for that. Like, doesn't need to be alcoholic. Like, just we don't have to get wasted. But yeah, you asking because you want to, right?
I think, okay, there is interruption.
You just finished it?
Okay, anyway, I was just a few consideration about that. And I'm finished. So thank you very much for everything in this webinar.
thank you all. Thank you, Mario. Thank you, Simone. So unfortunately, I saw there was a lot of interaction also from DLR now. So we wanted to have longer discussions. Unfortunately, we have to close this meeting as it was supposed to be 1 hour. But I understand the audience is more interested into the technical topics. For your information, indeed, we'll have the 5th webinar, which will be a bit different, because we will touch upon the Robinson and its training module on the lifecycle assessment. So you also receive some information in the forthcoming days, and you will also receive the invitation to join the upcoming training. Whilst we are looking forward to welcoming you to this event at the end of October, we intend to thank you for your active participation at today's meeting. And once again, thank you, Mario. Thank you, Simone, for your availability and also willingness to present at today's meeting. Thank you very much. And seeing you to the next webinar, and to my Robinson colleagues, see you in 2 weeks in Stavanger.